Okay, if we take a look at the position time graph here, we've got an object's motion over time, and you notice it starts flat, so it's not moving much, and then it slowly increases, meaning it's moving with a positive velocity for a while. Then it goes back to flat, so it slows down, stops, and then starts moving backwards, so back towards the origin, so it's moving with a negative velocity for a certain amount of time. So if we wanted to find the average velocity of this object over a certain time interval, let's just say from time 1 over here to time 2, we've already learned that if we just find the slope of the line that connects these two events, it should be delta x over delta t, that will give me the average velocity over this time interval for the motion of this object. Now, notice this line is an average of the increasing part plus the decreasing part. So it doesn't fully really represent the curve. It's the average of the curve. Now what happens if I were to zoom this time interval down into a shorter time interval? So let's just move this one up a little bit and move this one back a little bit. So I'm basically scrunching down the time interval. Again, the average velocity between the new time 1 and time 2 would be the change in position over the change in time, or the slope of the line connecting. Now, as I zoom this kind of close, these points closer together, as I decrease the time interval, notice the slope is getting closer to the shape of the curve. So imagine I were to decrease this time interval kind of infinitesimally, so getting closer and closer to a single instant in time. What would the slope of my line look like? And so as I decrease the time interval down to a single instant in time, the slope and therefore the average velocity of my object is what we call the tangent line, which is, imagine if you were to zoom in on this point in the graph infinitesimally. You zoomed in and zoomed in until it looked like a straight line. What would that look like? It would look like a line that just touches the curve, but if you zoom this in right on that spot, it would look like a straight line. So this is how we find the instantaneous velocity of an object that's moving. It's the slope of the tangent line at any point of the x versus t graph. So if you look at this portion of the graph here, the closer you get, the smaller time interval you get, the more the average velocity becomes the same as the instantaneous velocity. Now, at time t0, so this is our time t0, the average velocity is just dx dt, or delta x over delta t of the tangent. So I would draw my tangent line and then find the delta t, find the delta x, and that rise over run will give me my instantaneous velocity at that specific point in time. Now, instantaneous speed, similar to velocity, is just the absolute value of the velocity. So if I'm looking at this point here and I find my slope is negative, because it's decreasing, my velocity, my instantaneous velocity would be negative, but the absolute value of v would be my speed, which would be the positive value. So that's how we identify the instantaneous velocity, or the velocity at a specific moment in time of an object from its position versus time graph.